everyone. Welcome to my first video in 2025, and this is Unit 6 AP Calculus AB on integration accumulation of change. So first is on definite integral. It's an accumulative sum with infinitesimally small increments that can be visualized as the area under a curve in single variable calculus. That's denotes as the integral. It looks like an S from a to b, and you have a function f that you're integrating in respect to x. So this dx is the small increment, and this whole thing here, it can be represented as a cumulative sum that f of x is what you are accumulating with a really small increment dx that you can visualize as the area under curve, which you have a rectangle. You have a bunch of rectangles that you are approximating integral. That a and b are the limits, which is the bound. This a is the lower limit, b is the upper limit. And this is actually called Riemann Sum, which we will cover it right now. Riemann Sum is a way to approximate integral using rectangles. And here's the formal definition of definite integral using Riemann Sum. That the definite integral from a to b of f of x dx is equal to the limit as n approaches infinity of the sum of I star at 1 to n of f of a plus I delta x multiplied by delta x. So if you expand delta x, it's actually b minus a over n. Delta x is the small increment. B minus a means the total range from a to b, and the n means the number of rectangles, and this is just the small width of the rectangle. So you can write it as the limit of n approaches infinity, the sum I equal to 1 to n of f of a plus I times b minus a over n times b minus a over n. This n is the number of rectangle here. Okay, so there are two different Riemann sums, and we'll cover about left and right Riemann sum right now. So the left Riemann sum is when the rectangle's height is determined by the left side of the rectangle. The right Riemann sum is when using the right side of the rectangle. The delta x at the outside represents the width of the rectangle. So the delta x is this thing. That's the width of the rectangle. And this part here, it's the height of the rectangle. So if you have let's say a graph like this, and you're having this rectangle here, this is delta x. This is f at xi. So this whole thing, f of a plus I times b minus a over n, is this height of this rectangle, and this b minus a over n is this delta x, the width of the rectangle. There are uniform and non-uniform partitions, where uniform delta x is a constant and non-uniform is not, which means that it might look, non-uniform might look like this, and uniform, this delta x is constant. And for increasing function, the left Riemann sum always underestimates, while the right Riemann sum overestimates. The increasing function left overestimates and right underestimates. And if you have a finite number of rectangles, that's n, and the left Riemann sum is the sum of I starting at 0 to n of f of x at xi delta x, which is equal to the sum from I equal to 0 to n of f of a plus b minus a over n times I times b minus a over n. And the next is the right Riemann sum. It's the sum of I equal to 1 to n of f of x of I times delta x. So it can be written as I from 1 to n of f of a plus b minus a over n times b minus a over n. And that's the right Riemann sum, and this is the left Riemann sum. And there's also called midpoint sum, where the height of rectangles depend on the middle of the rectangle. So it's depending at the x value, where xi plus x of I minus 1 divided by 2, which is the middle value of the size of the rectangle. So what it means is that we have a curve like this, and this is xi minus 1, and this is x of I. The midpoint sum is depending at the middle point here. It's right in the middle of the two. And the rectangle is something like this. It's usually more accurate than left and right Riemann sum. And it can be written as I minus 1/2 when in this summation notation. And the summation notation for midpoint sum is the sum from I equal to 1 to n of f of a plus b minus a over n times I minus 0.5. Remember, the I is just the index of the rectangle, and you're subtracting by 0.5, which means that you're shifting by 0.5 to the last rectangle, the middle of the last rectangle. And trapezoid sum is when the approximation of trapezoid, where the endpoints are the 2 points of xi and x minus I, and connected by a linear line segment to form a trapezoid. So this means is that still have the same curve. You got point A, point B. Actually, let's call it xi minus 1 and xi. Or trapezoid sum is you're connecting it by a straight line. And you're forming a trapezoid like this. This is usually more accurate than left and right Riemann sum, and most of the times it's more accurate than midpoint sum. And the formula for trapezoid sum can be written as summation notation called sigma from I equal to 1 to n of f of x of I plus f of x minus 1 over 2 times delta x, which is equal to the sum of I equal to 1 to n of f of xi plus f of xi minus 1 over 2 times delta x, which is b minus a over n. And if you expand this, that's equal to the sum from I equal to 1 to n of f of a plus b minus a over ni plus f of a plus b minus a over n times I minus 1 over 2 times b minus a over n. And that's the trapezoid sum in the summation notation. And the next one is fundamental theorem calculus. And there's two parts of fundamental theorem calculus. And the first FTC is if we have a function, that function of the area is defined as the definite integral like this. And with the variable upper limit, it accumulates area under a curve from a fixed value a if f of x is continuous at close interval AB, then the derivative of this function is the derivative dA of x over dt is equal to the derivative respect to x from a to x of f of t dt, which is equal to f of x only when x is an element from a to b. So basically, if you have a to x and you're taking the derivative respect to x, then you can just switch the variable from whatever is inside, which is t for this example, replace with your upper limit, which is x. And if your upper limit is g of x, then the derivative of this d8 of x dx should be dx of is equal to the derivative dx of integral a to g of x of f of t dt is equal to, we need to apply the chain rule here, it's f of g of x multiplied by g prime of x, and what happens when upper and lower limits are both functions, it's the derivative respect to x from h of x to g of x of t dt is equal to the derivative of integral from a to g of x f of t dt minus the integral from a to h of x of t dt. And that's the first fundamental theorem of calculus. And now we will discuss the properties of definite integral. So first one, the sum rule and difference rule. It's the same as derivative. If you have f plus or minus g of x, it's equal to the integral of f of x dx plus the integral g of x dx. And same for the constant scalar rule. You can put the k outside. And if you switch the bound from a to b to a, you need to add a minus sign. And if you have the definite integral from ab plus the definite integral from bc of the same function, that is equal to the definite integral from a to c. For this one where the limits are the same, then it must be equal to 0, because if you think of the rectangle way, that the delta x is equal to a minus a over n, no matter what your n is, at least it's not 0, then this must be equal to 0. So the total area is equal to 0. And if you have f and g, which both are integratable, then, and the f of x is less than or equal to g of x for all x, then the integral must be less than, integral of f of x must be less than or equal to the integral of g of x. And when there's a removable or jump discontinuity, you can still express from, if you have a removable or jump at x equal to d, you can still express the definite integral from a to b. It just, you have to split into two parts from a to d plus d to b, where you have to assume that a is less than d, which is less than b. And this is talk about second FTC. This is probably the most important one. That if f of x is continued on AB, which it has a antiderivative capital F of x, and the antiderivative it's just the derivative of the antiderivative equal to the original function f of x. Then you can say the indefinite integral, something called indefinite integral. Actually, no. You have a definite integral from a to b of f of x dx is equal to the definite integral from a to b of the capital f of x dx, which is equal to f of b minus f of a. So what happens here is that the derivative of the antiderivative is equal to the original f of x, and when you integrate of a derivative function, it will give you the original function. And if you have the derivative of the integral function, it will give you the original function f of x. If derivative of g of x equal to f of x, then g of x is the antiderivative of f of x. And this integral without the limits is called the indefinite integral. The result is the antiderivative. And with a constant c, this is because a derivative of a constant c is equal to 0, that when you take in the integral, you don't know what the constant is, because the derivative already make it 0. So you have to plus c. And here are some common indefinite integrals. And still the scalar property, the sum and difference property, it's applied for all operators. And this is the reverse power rule. What we see here is that if we take the derivative of this antiderivative, this whole thing is the antiderivative. If we take the antiderivative for it, which is n plus 1 times x to the n plus 1 over n plus 1, which is equal to x, this one have to subtract by 1, so that's x to the n. That gives you the original function f to the n. And when n is equal to minus 1, that's equal to the natural log of the absolute value of x. The problem is that the natural log function is defined for x is greater than 0, but 1 over x is defined for all real number besides 0. You have to put the absolute value sign here to make up the domain. Antiderivative of the cosine equal to sine, indefinite integral of sine of x equal to minus cosine of x. The antiderivative natural log of x equal to x times natural log of x minus x plus c. The indefinite integral for tangent of x is the natural log of secant of x, which is equal to the negative of the natural log of cosine of x plus c. And there's more and more. Indefinite integral cotangent is equal to natural log of sine of x, which is equal to the negative of the natural log of cosecant of x. The indefinite integral of secant squared of x equal to tangent of x. Indefinite integral of the cosecant squared of x equal to negative of cotangent of x. Indefinite integral of secant times tangent equal to secant of x. Indefinite integral cosecant times cotangent equal to negative cosecant. And this is interesting for e to the x, because the derivative of e to the x is also equal to e to the x, and e to the x never change. And the integral of a to the x equal to a to the x divided by natural log of a plus c. And this expression here, that's the derivative of arcsine of x, which you take the indefinite integral, that will give you the arcsine of x. And which you see here, you can actually put the dx in the numerator if you want. Indefinite integral of 1 over 1 plus x squared equal to arctangent of x. and indefinite integral of 1 over x times x squared minus 1 over the square root is equal to arcsecant of x. You can actually write it as the absolute value, but it doesn't really matter for integral. And taking indefinite integrals into substitute f of x, capital F of x, and for the result, and ignore c, and c is only appear in the indefinite integral. And this capital F of x, you can use the second FTC to solve for the definite integral. There's something called U-substitution, which is the inverse of chain rule, to identify the inner function u that's inside of an outer function, and the outer function multiplied by the derivative of u. So let's say you got an integral of f of g of x times g prime of x. If you got some function like this, then you can say that u is equal to, actually let's do f prime. It doesn't matter because f or f prime is just a function. U is equal to g of x. To set u is equal to g of x, and du is equal to g prime of x dx. Then you can just substitute, then it's the definite integral f prime of u du, and you're solving for the indefinite integral of f prime. And for definite integral, you can change the limit by substituting the limit into u function, which we set it here. The upper limit, you can, if you have an upper limit a, then you, after your substitution, you can change the limit to g of a. And or you can do is calculate the indefinite integral first, then substitute u back and use the original limits. And if du has an extra scalar multiple, that include the scalar in the original function and multiply by the inverse in the outside of the integral. If you have a linear function which u is equal to mx plus b, then du is equal to m dx. But sometimes if you do this mx, some function f of mx plus b dx, you don't have a m outside. What you do is you multiply by 1 over m times m of f of mx plus b dx. Now you can do the u substitution. And next one is using long division. When this will happen when you're doing integrating a rational function, you do first is simplify, then use the long division to get a resultant polynomial with a remainder. What you will do is use the property that the sum property, and you're gonna separate the polynomial, and then for the remainder part, you'll either use U-substitution or other methods. And for example, the denominator is linear, then use U-substitution. And when it's a squared plus u squared, and which is equal to k over a times arctangent of u divided by a, that has a scalar k outside. And the last one is completing the square. When the problem is given 1 over quadratic or 1 over square root of quadratic, then you can use completing the square. So what you're going to do is you first convert into this form, and then you can use substitution to solve, or you can just directly write something like this. For this one, if you want to do substitution, you can do du over u squared plus 1. You somehow convert this to this form and use u substitution, or you can just directly write it in this form here. And when the problem is 1 over square root quadratic, then what you're going to do is convert into this first and solve for the integrand, which looks like this. And that concludes my review video for AP Calculus AB Unit 6. Please like and subscribe my video, and I'll see you next time.